of space. Let us see what is the T2 space. T2 space, T2 space or a Hausdorff space. A topological space X tau is said to be T2 or Hausdorff if and only if distinct points are separated by disjoint open sets. So what is the meaning of this? That is, for all x comma y belonging to x such that they are distinct, there exists two open sets. There exists two open sets, say u and v, such that x belongs to u, y belongs to v, and u intersection v is null. So distinct points are separated, x belongs to u, y belongs to v, separated by disjoint open sets. Okay, then let us see what is a compact space, because there is a theorem going to come now, okay, on compact space. What is a compact space? A topological space X tau is said to be a compact space if and only if every open cover has a finite subcover. Every open cover has a finite subcover. Now we shall go to prove a theorem now. The theorem is compact subspace of a Hausdorff space is closed. We shall prove the theorem compact subspace of a Hausdorff space, Hausdorff or T2 space. Okay, a compact subspace of a T2 space is closed. This is the theorem we have to prove. Okay, theorem. Now proof. Yes. So what is given, we'll write down. So let X tau be T2 and take a subset of X and that A be compact. So that's what is the first part. I've taken a Hausdorff space, that is T2 space, and I want a subspace, so okay, subset is taken A, and that subspace is compact, so is compact. Okay, what we have to prove? To prove that A is closed. To prove that A to show that A complement is open. To show that A complement is open. That is, we shall prove that A complement is neighborhood of each of its points. Each of its points. Let us prove that A dash is neighborhood of each of its points. Okay, so let us take any point belonging to A dash. Fine. We have to prove that this A dash is a neighborhood of X. What is a neighborhood? So if A is a neighborhood of a point X, if there exists an open set, if there exists an open set, okay, U, such that X belongs to U contained in A. So U is in between. So for every X, this A is said to be neighborhood of this X if there is an open set in between X and A. We have to prove A dash is neighborhood of X. I've just taken one point. See, each of its points. So I've just chosen one point. We have to prove that this A dash is neighborhood of X. That means in between these two, I want an open set. I want an open set between these two. Okay, now choose Y belonging to A. See, our x is in A complement and y belongs to A. So clearly x not equal to y, definitely. And where are x and y actually? X is coming from A dash and y is coming from A. Both A and A dash are subsets of x. So both are from x only. And our x is T2. Our x is T2. Remember our x is T2 and A is compact, isn't it? So our x is T2. Because it is T2, what? There exists two open sets. There exists two open sets. We'll call them as U and Vy such that separating x and y. So x belongs to U, y belongs to Vy, and of course they are disjoint equal to null. Okay, so now this happens for any y belonging to A. This thing will happen for all y belonging to A. Now we'll varying y in A. X is fixed in A dash. Our x is fixed. Okay. And we are varying y in A. So for every y, there is happening like this. I have got two open sets, U and Vi, they are disjoint and separating x and y. Now we are varying y. So for y1, okay, and x, for y1 and x, there exists u1 and vy1 such that they are disjoint and separating x and y1. Similarly, for the same x and next point y2, I get another open set, another set u2 and vy2. And similarly, for x and y3, I get u3 and vy3 and so on. Okay, just watch them. How are ui's and vy's? They are disjoint, these two are disjoint, these two are disjoint. Similarly, all other. I'm getting a pair of open sets like this. See, varying y in A, now take all these open sets. Okay, let us take all these open sets where y1, y2, y3, they're all coming from A. y1 belongs to this, y2 will belong to this, y3 will belong to this. So I've got an open cover for A. Got an open cover for A. So varying y, we are getting an open cover. Okay, so that is Vy. Okay, where is our y? Y is varying in A. Is an open cover for A. Open cover for A. And what do we know about A? A is compact. Remember, our A is compact. And we know that a compact space is nothing but what? Every open cover has a finite subcover. That implies this open cover also will have a finite subcover. So A will be contained in union I equal to 1 to n. So finite number of them, Vi. Okay, and let us call this as some V. Fine. So what have we got? That is A is contained in V. Contained in V. What is V? V is union of open sets. So V is open. V is open. And take the complement here. So therefore, V complement is contained in A complement. Remember this, we are going to use this. Okay, we got V complement is contained in A complement. Okay, so now remember we had taken only V y i's. Okay, now take the corresponding open sets of x. So what are the corresponding open sets of x? See, we had u1s, u2, etc. So consider the corresponding open sets. And all the open sets contain X. So take the corresponding open sets of X. Okay. And they are nothing but UIs. We have called them as UIs, which are nothing but UIs. And UIs intersection VYI. They're all disjoint. Okay. And X will belong to all UIs for all I. Remember, I had got U1, U2, U3, E4, etc. Yes. So now, let U be equal to intersection I equal to 1 to N UIs. I don't want all UIs. I'll take only 1 to N's. I equal to 1 to N. And intersection of UIs, I equal to 1 to N. Let me call it as U. Okay. And all UIs are open sets. All UIs are open sets. And finite intersection of open sets is open. Therefore, U is open. U is open set. U is open set. Okay. And very, very important, X belongs to U. X belongs to UI for all I. So therefore, X will belong to the intersection. It is there in all UIs. So therefore, X will belong to the intersection. Right? And what is U here? U is an open set. So I got an open set. Okay, I got an open set of X. Okay, so now, next we shall prove this is the open set contained in A complement. Let us prove that this is the open set contained in A complement. Okay, next, to prove that U is contained in A complement. Remember, we had to prove A complement is neighborhood of X. See, I'm getting an open set in between X and A complement. The only thing is I have to prove that U is contained in A complement. Okay, yes. We have to prove this. Yeah, so next. UI intersection VI. UI. We have this UI intersection. We have UI intersection VYI is equal to null. Correct? No? So where are UIs? UIs are definitely in VI complement. Following? For all I equal to 1 to N. For all I 1 to up to N. We are interested only in 1 to N only. Right? Now, we'll take the intersection. I equal to 1 to N UI is contained in intersection I equal to 1 to N VYI complement. Okay. Next, this is nothing but we have called it as U. U is contained in this one. We'll write like this. UYI whole complement. Okay, this we have called it as V and complement as it is. So what have we got? We have got U is contained in V complement, and remember V complement is contained in A complement. So therefore we got U is contained in A complement. So what have we got now? X belongs to U and U is contained in A complement. And what is U? U is an open set. U is an open set. So between X and A complement, I got an open set, U in between. So therefore, A complement is neighborhood of X. Neighborhood of X. And this happened for every X belonging to A complement. So therefore, A dash or A complement is neighborhood of each of its points. It happens for all X belonging to A complement. So each of its points. So therefore, A complement is open. A complement is open, therefore A is closed. A is closed, hence the theorem. Hence the theorem. What is the theorem we have proved? We have proved that a compact subspace of a T2 space or a Hausdorff space is closed. The proof of this theorem is completed. Now we shall go to the next theorem. The next theorem is another simple theorem. It says like this. Theorem is this. Let us read this. A continuous injective map from a compact space. Continuous, injective, continuous. Let us underline the words, the keywords. Continuous injective map. Okay, injective means 1, 1. From where to where? From a compact space onto a T2 space, Hausdorff space or T2 space, is a homeomorphism. Is a homeomorphism. Proof. Proof. Okay. So what is given? Let us write down. So what is given? We have been given a compact space. Okay, we have been given a compact space. So let X tau be compact. So injective map from where to where? Compact to Hausdorff. And Y tau dash be T2 or Hausdorff. Okay, T2 or Hausdorff, both are same. And we have been given a mapping from where to where? From the compact space to Hausdorff space. That is X tau to Y tau dash. We have been given a mapping. And they say this mapping is injective. That is 1, 1. Okay. And also they say it is onto. So and onto. Injective and onto, done. And also it is continuous. And it is continuous. We have to prove that TPT to prove that F is a homeomorphism. Homeomorphism. What is a homeomorphism? We have to prove F is bijective, F is continuous, and F is an first one. Clearly, F is bijective. Why it is bijective? Because they have given. They have given it is 1, 1 and onto. Therefore, it is bijective. The first one is given. We'll call it as 1. And also, second point, clearly F is continuous. Is it continuous? Because they only have given. That is also given. That is also given. We'll call it as 2. Then, what else we have to prove now to be a homeomorphism? To show that F is an open mapping. F is an open mapping. We have to prove that F is an open mapping. That is, we have to prove that takes open sets to open sets. Okay, so let me take any open set in the domain. So what is the domain of F? The domain of F is this. So I'll take any open set here. So let G be an open set where in the domain X. So let G be an open set in X. So what about its complement? So X minus G is dash in X. Can you guess? G is open, complement is closed in X. And what do we know about X? X is, they have given what? X is compact. X is compact. We know that a closed subspace of a compact space is compact, right? So this implies X minus G is compact. X minus G is compact because of using a theorem which says that a closed subspace of a compact space is compact. So therefore, X minus G is compact. And F is what? F is